gentlemen, and welcome to the Oxford Martin School. It's wonderful to see such a packed hall for what's going to be an absolutely excellent lecture by Dr. Eric Drexler. The seed for molecular nanotechnology was initially sowed by Richard Feynman in his famous 1959 lecture, Plenty of Room at the Bottom, but where he described what amazing things could be achieved if we could just manipulate and construct matter from the atomic and molecular scale up. But it was Eric Drexler who took that seed and grew it into what became a vision and a call to arms. In 1986, he released the book Engines of Creation, a remarkable book which inspired a generation of scientists. In it, he describes in detail the potential for nanoscale factories, which could build a remarkable range of products from simple starting materials, cheaply, quickly, and with properties we cannot presently achieve. In ways, this is a little bit like what ribosomes do inside our cells, but with all the advantages conferred by inorganic materials. Now, somewhere along the way, nanotechnology came to mean a much broader range of things, basically anything with nanoscale properties. This includes materials with remarkable properties like graphene and carbon nanotubes, and much more mundane things like sunscreen and toothpaste. Focus shifted away from the original vision of molecular manufacturing, or atomically precise manufacturing, as Eric now describes it, which wasn't achieved. However, Eric, in the intervening years, has had the intellectual tenacity to stick to his guns and to tease out the steps needed to develop this technology, atomically precise manufacturing, figuring out the proofs of principles that are needed along the way, and monitoring progress across the range of different fields that will be involved in developing this technology. And along the way, he wrote this remarkable book, Engines of Creation, or not Engines of Creation, I'm sorry, Radical Abundance, which he'll be talking about today, where he explores how atomically precise manufacturing could revolutionize manufacturing as exists today and utterly transform the material basis of our civilization. He's also well aware of the risks of any powerful technology of this nature and has discussed this at length with us at the Oxford Martin programme on the impacts of future technology. I have to mention that Eric is by no means a one-trick pony, having spent in office with him for 2 years. He's just incredibly knowledgeable about an entire range of fields, including synthetic biology, computing, cyber defense, synthetic biology, and he's guided our thinking on these topics a great deal in the last 2 years. And I'd really love if sometime in the future you might give talks on these topics as well. In fact, I think it'll probably be one of my dying regrets that I've spent more time in Eric's company answering boring emails than gathering insights from him. But today's lecture and today's story is that of atomically precise manufacturing. And the only man to tell it, and indeed the man who is writing that story, is Dr. Eric Drexler. Eric.
Thank you, Sean, and thank you all for being here this afternoon or evening. It's a pleasure to have an opportunity to speak with you, and it has been a pleasure being at the Oxford Martin School and the program on the impacts of future technology. I was invited here to finish work on the book and now plan to stay long term. No particular plans to be elsewhere. As I like to say, I love the climate at Oxford on the intellectual side at least, though having come from California, I had to learn things about warm underwear and thermal socks before I was really adapted and able to survive the winter. So this being about the book, I would like to read a few paragraphs at the beginning and at the end a couple more. So I won't be doing much reading, but my wife said, oh, you must. So imagine what the world might be like if we were really good at making things, better things, cleanly, inexpensively, and on a global scale. What if ultra-efficient solar arrays cost no more to make than cardboard and aluminum foil, and laptop computers cost about the same? Laptop supercomputers, excuse me. Now add ultra-efficient vehicles, lighting, and the entire behind-the-scenes infrastructure of an industrial civilization, all made at low cost and delivered and operated with a zero carbon footprint. If we were that good at making things, the global prospect would be not scarcity, but unprecedented abundance, radical, transformative, and sustainable abundance. We would be able to produce radically more of what people want and at a radically lower cost, in every sense of the word, both environmental and economic. This isn't the future most people expect. So, my purpose with this book has not been to persuade people that this is a picture of the future and everyone should run around saying, radical future, radical future. My purpose is to open a conversation on this subject, to say that there is a very credible prospect of a very different set of technologies emerging that can transform the material world in a way that's much like the way that digital electronic technologies have transformed the world of information. In fact, the analogies run rather deep. So the purpose is to open a door, to give a sense of what appears to be there, and to suggest that we need to talk about it. So toward the end of the talk, I will return to this slide. I will, in the intervening parts, spend some time talking about molecules and little things, but this is not about small things. It's about large things. It's about the future. It's about the problems at the scale of global economic development, resources, greenhouse gas accumulation, climate change. And increasingly, as I just look at problems that people talk about in the world, if a problem can be addressed or substantially solved by means of manufacturing, there's a sense in which it can be called a manufacturing problem. And this is an example. Global warming is an example of a manufacturing problem. The most obvious sense of that is that the main barrier to rapidly deploying renewable energy sources like photovoltaics and displacing the existing carbon infrastructure is a problem of the cost of making devices that can be made today and are either being deployed already at relatively high costs or have been made in the laboratory and not yet commercialized. If we could make those sorts of things at a very low cost, the problem would look very different. And I will take a step further and explain how the problem can actually be made to reduce at a rate much faster than geophysical processes would enable. So the book has a range of topics. I've put in blue some that I'm going to say something about in the talk. Origin of ideas, a very concrete sense of the look and feel of the nanoscale world in a mechanical sense. The notion of science defining a timeless landscape of technology, not projecting what people will do, attempting to predict commercial products, but instead asking, what do the laws of physics tell us about patterns of cause and effect in the world? What can be accomplished? What kinds of devices can exist and operate? Which is a question of physics. The answers are the same today as they will be in 1,000 years, and the same as they were in galaxies far away and long ago. The rules of physics have not changed, and therefore the emergent structure of the potential of technology is timeless. So after saying a bit more that's specific about atomically precise manufacturing, I'll then ask what can we do with that, and at that point I think be in a position to say something about changing our conversation about the future. So where I began is sort of curious. It's very far away from atomically precise large-scale manufacturing and has a lot to do with what Sean mentioned in looking at molecular biology and in particular ribosomes. Ribosomes are programmable molecular machine tools. They take in genetic information, 6 bits at a time, and direct the assembly of protein molecules. And as an undergraduate at MIT, then studying space systems engineering, in particular the potential of manufacturing in the space environment with space resources, it was natural to ask, well, molecular biologists are finding all of these little atomically precise molecular machines. Well, what can they do? Well, biology demonstrates a lot of what they can do. What could we build with them? The answer is better machines. And as a starting question, can we learn to design and make these protein-based machines? Well, the reason that's interesting is that proteins are not, like pieces of meat. They're not soggy, soft things. They're an engineering-grade polymer. The horn of a bull is a protein. It's a keratin. And if you confuse that with a piece of meat, you're likely to have if you're a matador, you're going to have the horn come into contact with your meat, and the horn will win, and you'll be very unhappy with what it's done to your body. So when you hear protein, don't think of meat. Think of sharp, dangerous things, and be concerned about it. Other proteins can be seen as an aerospace-grade biomaterial. So in 1981, I published a paper in the U.S. Proceedings of the U.S. National Academy of Sciences, which said to the scientific community, you've been trying to understand how natural proteins fold, and postponing work on designing proteins that fold in a predictable way because they were both of these problems were confused and conflated as one problem of protein folding. And the paper drew a line and said there's the scientific problem of predicting what nature does, and the very different engineering problem, same material, same physics, same chemistry, but a different problem of designing a molecule that will fold predictably. And that was soon dubbed in follow-on papers, dubbed the inverse folding problem, led to a growing literature, and ultimately to a range of successes. And this particular structure is a milestone that happened a number of years ago, about a decade ago now, which was the design of a protein that was more stable than natural proteins, designed in atomic detail. Being able to do this is now a very routine activity. So the paper said, protein engineering is promising, it's now a field. The paper, however, went a bit further than that. It asked, where can we take these technologies in using tools to build better tools and extending the scope of design? It's important to recognize that atomically precise fabrication has come a very long way already. Back in 1828, the state of the art in fabricating organic molecules was urea, which is 8 atoms. As of a few years ago, the progress had passed the 1,000,000 atom mark, and there is now routine technology for fabricating with DNA, 2-dimensional and 3-dimensional objects that have remarkable control of shape. It's essentially you draw a picture and you think of it as a set of pixels, molecular pixels. You pick the right DNA strands, mix them together, warm it, cool it, and they go together to make the desired structure. So it's a very powerful technology, and the challenge now is to learn to apply that kind of control at that scale to a wider range of materials. And as we do that and begin to use those tools to accomplish tasks like what we see ribosomes doing, but making a wider range of materials, well, it raises the question, which I began to think in terms of very explicitly some time ago, of where technology can lead. If you iterate this process using tools to build better tools, well, starting with blacksmiths, they got the Industrial Revolution and landed on the moon. Where can you go if you apply this line of advance in the molecular world? And that leads to this question that I alluded to earlier of what do the laws of physics permit? What's part of this landscape of physical technologies? So I like to think in terms of this diagram. On the lower left is sort of the minimal capabilities. You're not really doing much of anything. And from there are various performance metrics. How fast can you move? How accurately can you measure? How much computation can you accomplish in a given volume with a given amount of energy dissipation? Many different engineering metrics defining a high-dimensional space of potential technologies. Then the question is, how much of that space does physics allow to be filled? And there's a methodology for answering questions about that. Some of the questions, carefully chosen questions that are designed, the questions are designed to be answerable. And that discipline is something that can be called exploratory engineering. And what that leads to is designs out here in possibility space that are beyond the boundaries of what has been demonstrated by engineering, but are by construction, by analysis, clearly within the bounds of what is physically possible. And as more of those are added, you can start to get an idea of a lower bound on some of the potential of a truly mature technology, the kind of technology that can be developed and applied by a species that has actually gotten good at making things. It isn't still running around hammering out pieces of iron, which is what a lot of our technology is still based on. Heat up iron, pound on it with increasingly, automated hammers and great precision. But manipulating matter at a level that does not reflect its actual detailed atomic structure. So, in looking at this area, it turns out there are a lot of discoveries to be made. And the reason for that, well, back up for a moment, is that this exploratory engineering domain amounts to really a cultural or societal blind spot in the world today. There's knowledge to be had there. You start with established science, deliberately excluding anything that's not textbook quality science as an initial premise for reasoning and analysis. Then apply engineering methods to describe potential systems. Well, describing potential systems using engineering methods, well, that's not science, is it? Science is about this new knowledge, expanding what's in the textbooks, and this is about applying knowledge that is not really of ongoing interest, except as a tool. Well, it's an engineering approach, but is it engineering of the sort that gets paid for? Well, explicitly looking at what can be built with tools that we don't have yet. And if you do that in a corporation context, well, you're wasting your time, you're wasting people's money. It's not supported. So we have an engineering methodology applied to established scientific knowledge. That is not something that is a professional focus for scientists. It's not something that's a professional focus for engineers. There is, however, low-hanging intellectual fruit to be had. One can choose designs for ease of analysis and reduce, in many cases, problems of feasibility to a set of problems that are the sort that you might find at the end of a chapter in a college physics textbook. And it's a matter of asking the right questions, recognizing that they can be answered, and then pursuing the answers and checking the numbers. So, in the atomically precise technology domain, both high performance and ease of analysis, not ease of construction, not ease of synthesis, we're beyond what can be made today. The most attractive area is strong covalent solids, things that have diamond and silicon atoms bonded covalently to make materials, or carbon, and silicon bonded to make materials like diamond carbon nanotubes, silicon carbide, and add bits and add mixtures of the light covalently bonding atoms. And you find that you can build a very wide range of structures. And what's nice about these is that they're very stable. Current methods for modeling molecular systems, standard methods that are used in chemistry, model them very well and can describe their mechanical properties. In addition, quantum chemistry methods where you have a well-defined geometry, not having to worry about a very large configuration space, not having the challenges of large entropic terms that are hard to calculate, but instead systems that actually are a sweet spot for the analytical tools, can describe the sort of control of fabrication that can be achieved by guiding the motion of reactive molecules. Kinds of chemistry that are seen in solution, but controlled by guiding the motion rather than allowing free diffusive motion dominated by thermal fluctuations. So here's a picture that shows atomically precise structures doing atomically precise manipulation. The structures have to be relatively stiff to keep the amplitude of thermal fluctuations small, and how small those can be can be calculated from the mechanical properties of the materials and elementary statistical mechanics. So there's a sweet spot here of atomically precise rigid structures that can guide the motion of reactive molecules to construct atomically precise rigid structures. That's somewhat analogous to our ability today to use metal tools to cut pieces of metal to make more metal tools, the kind of technologies that you find at the core of our industrial infrastructure, the machines that make the machines that make the machines. So abstractly analogous to that, but an atomically precise domain where you're not cutting metal, instead you're assembling molecules and molecular fragments. So the discovery was that one can do design and analysis very reliably with present-day tools of rigid atomically precise machines that can't be built yet, and that these can be very much like familiar machines at a macroscopic scale. So here's some different kinds of gears that are used to transfer motion and power in machine systems. They make a nice test case for designing atomically precise systems because they have lots of moving parts, and you could characterize their stiffness and efficiency and internal friction and various engineering parameters. And it turns out that point by point, one can design strong covalent solids. Each of these little spheres is, of course, an atom. The red ones are oxygen, the yellow are sulfur, the darker ones, nitrogen, carbon, and silicon. Those tend to be hidden inside because they're tetravalent. And you can apply standard molecular dynamics methods and get a picture of how they operate. So why is this interesting? Well, having atomically precise control extended has been very useful in technology for a long time. It's what chemistry and material science are about, and it can be seen as an advanced form of the sort of control that people attempt to get by cutting pieces of metal and shaping ceramics and silicon precisely. But in addition to that, it turns out that there are advantages in productivity. It turns out that fundamental mechanical scaling laws make it very natural to think in terms of the same velocity in meters per second of small structures and large structures. Motion times are proportional to scale. Half the distance takes half the time to cross at a constant velocity. That makes the operating frequencies inverse to scale. And if you have a linear scale down of the linear dimensions by a factor of 1,000,000, frequencies increase by a factor of 1,000,000. And in fact, that is pretty much where one gets to with these structures. In fact, factors more like 10 to the 7th. So you can take what's known in mechanical engineering, and here's where the enormous leverage comes from. You can take knowledge in mechanical engineering, which has already shown that it can be transferred from one kind of metal to another kind of metal to plastics, to ceramics, large scale, small scale, huge range of products. That knowledge, that engineering knowledge, and the knowledge of the kinds of systems that can be built from those kinds of components transfers into the nanoscale, given the fabrication technology to make the components. And if you do that, you get increases in frequency by a factor of roughly 10,000,000. And as a consequence, the mass throughput of a mechanical manufacturing system on that scale, mass per unit time per unit mass of equipment, if you think about it a bit, the proportions and so on, you get an increase in that measure of productivity of a factor of 10,000,000. Now, the last couple of times we've gotten, or a few times we've gotten factors of 1,000,000 or 10,000,000 in technology, the three that I can think of are from chemical to thermonuclear explosives, is about that kind of factor. From being able to travel around the world to having instruments plunging into interstellar space is a similar factor in distance. And the advances in computation from hand machines up through today's computation is in excess of that. Now, all of those have made some difference in the world, and none of them were as fundamental as a transformation in our ability to make things. Blowing things up has very limited utility. Making things has a lot of utility. So it's an old story. Mechanical engineers know that if you have a suitable range of devices, gears and bearings and conveyor belts and shafts and motors and 4-bar linkages and toggles and all these other gadgets, you can make machines. The machines could be used to make the machinery necessary for factories, move parts around from place to place, put them together to make larger assemblies, put those together to make yet larger assemblies. So don't picture making big things atom by atom or molecule by molecule. Instead, think of taking molecular scale building blocks, putting them together to make larger building blocks, then having larger machines that put those together, and so on, where 30 stages of binary assembly, 30 doublings, crosses the gap from nanoscale to meter scale, ton scale objects. So convergent assembly. Familiar story? It transfers. As I say, I was thinking about these things when I was doing systems engineering at MIT, and it's very much a systems engineering approach to thinking about what is possible. In the book, in addition to making some of these physical facts, I think very vivid and concrete, a point that I return to is the analogy between these systems and digital electronics. And that analogy has some deep physical parallels to it, but just a number of features here. In one case, you have arrays of nanoscale electronic devices, gigahertz frequencies, working with bits and bytes and processing information in a general purpose way. Direct parallel. Mechanical devices instead of electronic. Mechanical devices are slower, so instead of gigahertz frequencies, you get megahertz frequencies as a convenient typical speed. Instead of discrete bits and bytes handled in a digital way, all or nothing, not not like in analog signals, which are a bit mushy, but discrete operations. Here, operating with the smallest bits of matter, again with discrete operations at the scale of atoms and molecules. And I should mention that just as machines usually process information in machine words or bytes, likewise one in the nanoscale world typically processes matter in molecules, not individual atoms, which are not very convenient. But one still end up with atomically precise results. So in the digital information world, we've seen general purpose information processing that would have startled people who were looking at information processing from a 1950s perspective, for example. I think there are a lot of people who thought that, well, yeah, you'd be able to have video phones, telephone linkages with video screen. Okay, that would be your video phone. And perhaps a digital camera system. Well, that would be some camera system over here with a bunch of equipment that would record things. And so on through information filing. Well, let's see, there was a proposal from Memex, which was a mechanical system like a little tiny bit of the web, and an endless range of special purpose devices. What would not have been guessed is that one would have something like a tablet computer that is a camera and a darkroom and a huge warehouse full of film and a storage system that indexes those things, and it's also a video phone, and it can also do computation for you, and it's also something much better than a pinball machine, and all this in one thin device that works with what? A general purpose information processing tool that forms patterns of bits and bytes in a fast, deterministic way by discrete means. So imagine that abstract pattern translated into the material world. I can't. One can begin to. I think it's better to try than not to try. But the potential of digital electronics is far beyond what anyone could have imagined in 1950s. There were some people who were imagining a remarkably large amount of it by 1970. But even those sorts of perspectives didn't see what we saw today. Around 1990, I was working with some people on a hypertext publishing technology before the web, and we never imagined anything like Google that could image the entire world, a large slice through the entire world of accessible information online and index it. We thought about much cruder ways by present standards of handling that information. So much is not seen. So, see, I've mentioned molecular level, atomically precise control. Some consequences. One is that a process like this can control all of the outputs, not just the desired products, but also the byproducts. Instead of washing with water and ending up with a dilute solution of toxic chemicals where it's either expensive to process or there's a temptation to dump it into a river, instead, byproducts can be precise structures themselves that are typically would be recycled as part of a closed loop, and if they're not, it would be because you had some materials that were put in that you didn't want, and you could put those aside in the nicest way that you can think of. See, mentioned rapid, low resource consumption. With much stronger materials and smaller, faster devices and more efficient engines, there are many consequences that flow from this. Need for energy for a given function can be reduced. The amount of mass needed for products can be reduced. And it turns out that the ideal materials to use are usually the light covalent elements. Even copper can be replaced by carbon nanotubes. And those are cheap and abundant. Right now, there are wars being fought in Africa, in part because there are materials like molybdenum and tungsten that have special, unique value in technology. The need for special materials like that apparently decreases greatly with this different technology base. And also radical and opening new realms of technology. I'll say just a little bit about that shortly. And as I mentioned, textbook physics, chemistry, elementary mechanical scaling laws. What I'm describing here can be checked. The people you shouldn't trust are the experimental scientists. They say, oh, I did something here, and then they publish a paper, and you can't check it without a whole lot of effort, and a lot of it turns out to be wrong. This is much more reliable. Calculations are laid out. They can be checked. But it's not part of science, though it's an application of scientific knowledge. And so scientists tend to be very concerned with what their next grant is going to be about. It's not within their professional competence or interest. And likewise, engineers, as I mentioned, are focused on different domains. And so there is this low-hanging fruit, this potential for radically different technology base that was analyzed by the US National Academy of Sciences. And, well, okay, just a little background question. Any sensible person with some sense of the way the world works has a heuristic. And one heuristic is that if you're hearing about something that is surprising and allegedly very important and allegedly the knowledge is lying around, well, it's probably wrong. I mean, you find something like that. You can find all sorts of things that have that feel on the web. They're usually not coming out of the Oxford Martin School. But it's appropriate to discount them. Well, I would just note two facts. One is this falls into a crack between science and engineering. And the other one is, and this is just a little point out of a larger discussion in a chapter titled, A Funny Thing Happened on the Way to the Future. There was a study by the US National Academy of Sciences, a report that said, basically checked the numbers, and said, this is a promising line of technology development. We should formulate and fund a development plan. This report was passed to an organization that had been part of a move to attempt to prevent that study from happening in the first place, and certainly didn't want to listen to the answer for political reasons. We've heard a lot about politics and suppression of science. It goes on a lot. This is an instance. And one of the consequences was that the executive summary was rewritten. The executive summary passed to the White House was rewritten to make the recommendation for research be attached to a different line of research. And this was not an accident. So the background observation here is, one, falls into the cracks, and two, there has been some politics behind this that has very interesting structure, and I don't entirely understand it, about 90% understand it. That has been a barrier between available knowledge and widespread understanding of it. So a hook, just a concrete kind of conceptual picture. Think of machines like 3D printers. They're boxes. They've got stuff inside, moving parts. They process materials. Digital information goes in, and what comes out can be any of a wide range of artifacts defined by a computational digital specification. Now, we see that in 3D printing. It's beginning to give us some hint of the potential for distributed, flexible, general-purpose manufacturing. Now, imagine that you had much higher throughput, lower cost raw materials, and outputs that instead of being plastic or a limited range of metals with relatively poor surface finish, were instead atomically precise structures of the best materials that can be made today and beyond that. That's something that has enough relationship to 3D printing that we can learn something from about this from 3D printing, but clearly goes far beyond that. So some known possibilities. There are a bunch of just obvious ones. That if you're able to make better materials and finer scale structures and do this inexpensively, well, you can do things like make computers. That's an obvious one for making small scale components. And state of the art not too many years ago was the IBM Blue Gene supercomputer, which weighed 100 tons and cost more than $250,000 and had not a whole lot more power than a stack of computers with graphical processing units these days, surprisingly. It consumed 5 megawatts. Well, physics promises us that we can build devices that have at least 1,000 times the, not speed per se, but data processing throughput, a tiny fraction of the power, tiny fraction of the mass, and a very small fraction, like 1/100 millionth of the cost. Costs typically come out to be something like, on the very rough order of a dollar per kilogram. And independent of the detail of the structure being made, because you're already building from the atoms up and having it be intricate features doesn't cost more than having a uniform material. So, aerospace. To date, aerospace systems have largely been made out of aluminum, been massive. It's very hard to make them precise enough and to be low enough defect rates and large enough margins of safety to be highly reliable, and they're very expensive. If you were working with carbon-based materials of the sort that are made in the laboratory, but you could make these materials on a large scale, things like carbon nanotubes in bulk. Massive structures in vehicles can be reduced to something like 5% of what it is today, and the cost per kilogram down by an enormous amount, and get reliable systems as well. It's been a long time dream of the human race being able to expand into the solar system. Some of the first exploratory engineering was done by a man named Konstantin Tsiolkovsky, who's known as the father of astronautics, and laid out a program for exploration and settlement of the solar system in the late 1800s, and got the basic facts right because he knew chemistry and physics. That dream of opening space beyond Earth has been around for a very long time. And the problem that has made that not happen, not the door not open, is a manufacturing problem. We're just barely able to make structures that are light enough and strong enough and reliable enough to get into space at great expense. If you're able to make different structures, all of a sudden the economics is different, and the world becomes much larger than the Earth. So that's one of many radical dimensions of a potential future. I mentioned some mention of the book discussing things that are not quite so nice. Applications in weapon systems are obviously enormous. Economic disruption is also potentially enormous. Just one point of reference is cost of manufacture. That alone is enough to expand arsenals by a factor of 1,000, very conservatively. Now, if one is thinking about international competition in the future, I think it's useful to look back in history and ask, well, think of the Industrial Revolution. There were some countries that were leading, and there were other countries that were not, and the ones that were leading dominated the world for a time. This is a similar kind of threshold in technology. I think it's possible, maybe even politically possible, for countries to be all on the same side of this one. There are some very strong motivations for doing that, though that's another story. That comes late in the book and builds on a lot of previous points. But clearly, there is the potential for an arms race that would push hard and fast and be extraordinarily disruptive. But some of the purposes of some of the things that are causing international stress today are things like climate change and limits to food production. And it turns out that that is also in part a manufacturing problem. Why don't we just raise the productivity of agriculture by a factor of 10 and decrease water consumption enormously and have less runoff of nitrogen and phosphorus, so less pollution of streams, and make it things that are much more independent of local weather and climate? Well, the answer is it's expensive to build enclosed agricultural systems. You can't cover 1,000 square kilometers with structures of this sort economically today. But greenhouse agriculture can indeed produce the kinds of advances that I just outlined. And if manufacturing made this kind of capital infrastructure truly accessible and affordable, world food problems would look very different. So it even extends to something as far away from molecules and boxes that make things, as far as food. So wrapping back to the point that I started with about energy. Today, silicon cells are rather expensive and fragile, though there are more and more technologies emerging. With this kind of fabrication base, one would be able to make tough, flexible materials that had lots and lots of small photovoltaic cells, rather efficient, the kinds of materials that could be laid down on the surface of a road. Think of a sheet of like a black plastic material that unrolls, conforms, adheres, is a tough, drivable surface, but is also an efficient photovoltaic material. The electric power requirements of civilization today can largely be supplied by resurfacing roads and roofs. So returning to global warming. And well, the current situation is that CO2 levels have been climbing like this. This is from the Mauna Loa Observatory, which, by the way, because of budgetary cuts in the United States, may be shut down. They're trying to raise money privately to maintain this particular data series. And everyone's expectation looks something like this. Very few people expect that in the next couple of decades we're going to do much better than to keep the rate of increase from increasing. And because constant emissions, to a first approximation, it accumulates. So if you were to flatten emissions entirely immediately, instead of having them continue to rise, CO2 levels would continue to rise, which is a problem I don't think the politicians understand, but that's another story. Even people who've come from MIT and have read the summary of an IPCC report that makes this fact very clear, if you ask them about their understanding, it turns out they think that the CO2 will go away if you stop emitting it as though it were SO2. So that is the expectation, and it's very nasty. You'd like to have a future that looks like this if you could, but that requires approximately 10 to the 21st joules of energy, free energy. That's the work of compression of the dilute CO2 gas. That's the excess of, in this time frame, the excess above industrial levels. And that amounts to about 30 terawatts of power for a year, or 3 terawatts for a decade. And 3 terawatts of electric power is about the total electric power capacity of the human race today. And this is why, when people talk about atmospheric carbon capture and removal, it's generally not very high on the agenda as something practical. But it's a manufacturing problem. If you were able to make solar arrays with about the area of that green square there, and use the energy efficiently in small devices that capture and pump CO2 molecules with good thermodynamic efficiency, that could draw down the excess atmospheric CO2 in about a decade. And so even the problem of CO2 in the atmosphere today can be framed as a manufacturing problem. I should hasten to point out, as I do in the book, no one should count on this. The time required to get from here to these technologies is unknown. And I very strongly discourage people from saying, oh, there's not a problem, we'll have a technological fix. I think, in fact, there's a very good prospect of that, but no one should count on it. And if anyone is in the world of green politics and would like me to jump up and down and say that people should not count on this, they can quote from the book, and I'm happy to provide some additional quotes going forward. So, about pathways, there is a fair amount understandable right now about how to get from here to there. Exploratory engineering can look at technologies that are a bit beyond what we've made today, but clearly accessible, can ask what can be built with those technologies a step further along, and identify a series of stepping stones that leads to a scalable, atomically precise manufacturing technology base that then enables a much larger range of what is possible to be accomplished. So where we stand today is that we have macromolecular engineering, this protein and DNA technology. We can now see in considerable detail how to bring those technologies together in a way that can't be done in one laboratory, but can be done by a collaboration of laboratories to build stereotactic, three-dimensional, precise controlled assembly systems working in solution, small scale, more comparable to a ribosome than to a great big box, but devices that can be made by chemical means 1 trillion at a time and can make structures that are beyond those accessible today, including better machines for accomplishing similar operations, but better. Therefore, leads a path leading up to more advanced forms of stereotactic assembly, scalable technologies at the level of what I've focused on in the talk, which then leads to revolutionary applications. So that, in broad outline, is where we stand today and the prospects and some of what it could mean for our future. So I think this puts the radical in radical abundance. And again, my aim isn't to say everyone should jump up and down and say radical things. I've sort of been stuck with that job, whether I want it or not. But I do think it's time to start changing our conversation about the future. And I would like to say to members of various research groups at Oxford that I would greatly enjoy engaging with these groups, research and policy groups, answering questions, and discussing how one can begin to engage with these topics in a way that is suitably moderate and incremental to fit into mainstream discourse, which is an important objective to achieve. More information. If you're interested in a big fat work of applied physics packed with equations and diagrams and specific atomically precise molecular structures and analysis of same, there is this book, which is the one that was the reference in the US National Academy's study that said we really ought to be doing something that the politics then said we wouldn't. This one is available. It's a PDF available for download. It's a technology roadmap that was developed in conjunction with several of the US national laboratories. Management on one side was Battelle, which manages research at a number of these national labs. I was the technical lead counterpart in that. Radical abundance, of course. And finally, getting back to Oxford Martin, there's a report, about 105 pages. It goes from the foundational level all the way through questions of arms control and changes in vital national interests and avoidance of needless risks going forward. So it's from hardware through policy. About 105 pages, and if you Google Nano Solutions, Oxford Martin, you'll find the PDF, and we'll have extensive reading available. Thank you.
So we have some time for questions. If you've been to some of these talks before, you know that how we usually like to do it is take 2 or 3 questions at a time, try to keep track of it in our heads, and answer them in turn. So please put up your hands if you have questions. Okay, I'm going to start with, I saw this hand, your hand, and yours, Ken.
And please wait for the microphone.
So there have been a lot of successful experiments, academic experiments in terms of manufacturing nanosystems, but I haven't seen a lot of commercial success. Why do you think that is, and when do you think we're going to have some commercial success in manufacturing nanosystems?
Well, this leads to a question of what do we mean by nanosystems? Today, the leading nanotechnology is something that has it's an industry on the scale of $100 billion. It's an enabler for an enormously large segment of today's economy, and it's responsible for the information technology revolution. It is not called nanotechnology. It is not called nanoelectronics for historical reasons. It's the semiconductor fabrication technology, which years ago went deep into the nanoscale range, with, in fact, in the gate oxides down to atomic precision in the thicknesses of them. So why do we call materials nanotechnology and these machines nanotechnology, but don't call semiconductor fabrication nanotechnology? And the answer is politics and marketing. And as for the things that are called nanotechnology, they're not what I'm talking about, and they're not the semiconductor technology. There is a lot of very valuable research. I think it's great. but it's not the same technology.
Question
Thank
at the back.
A few decades ago, there was a scientist you'll be familiar with who predicted that nanobots would go into the wild and take over the world and turn everything to grey goo. What made you change your mind?
Well, actually, I didn't change my mind, but my thinking on this, as expressed in Engines of Creation, where I mentioned the term grey goo about 3 times in about 2 paragraphs, and then went on to say, this isn't a problem because one does not need to do anything that runs such risks. And then in 1992 went further and said there's no need to do anything remotely like small machines that build copies of themselves. So that's what I said. What the Omni magazine said to 1 million people, 1 million science-aware, somewhat flaky readers in the United States in 1986, was worry about grey goo. And everyone said, it's Drexler's idea. And the media ran around and pointed to it because, hey, it's good to talk about things that are scary. It was great for science fiction authors. It was great for internet chat. And it then made scientists who were doing things that they called nanotechnology afraid to be associated with small machines because small machines were equated to little tiny robots that might eat you, which is a bit bizarre. Large machines aren't large robots that eat you, so why are small machines small robots that eat you? I don't know. And that led to some of the political meltdown that came later. The only scientist I know who said that if you built small machines that could move molecules around, that would mean little tiny machines that might eat you, also said, but you're safe because it's impossible. And that's a Nobel laureate who really muddied the waters by grossly misrepresenting the ideas in the pages of Scientific American in an article where I had another article pointing out that one's not talking about this technology, but talking about something else. But of course, it's the other article that gets cited, and we're still living in the aftermath of that particular piece of intellectual disruption.
So if you had the resources of, say, a Bill Gates, $100 billion, would you put all of it into research along these lines to kind of move the world sooner and closer to this, or is it that, or would you do, what would you do if you had the resources?
If I had the resources, there are a lot of things that I would want to do. I have a lot of interests that aren't in this area, but have instead more to do with improving how society processes information and maybe perhaps improve contact with reality in public discourse. But it's a separate topic, though largely stimulated by what I've seen here. I would begin to ramp up a program that started in 2 different areas that would converge. One would be to fund the development of very effective computational design tools, taking the mature computational methods used for describing molecular reactions. That's quantum chemistry. Density functional theory is pretty good for a lot of it. The coupled cluster techniques turn out to be exquisitely accurate these days, at least by the relevant standards for small structures. Build on those design tools that we see in computer-aided mechanical engineering design and computer-aided electronics design, bring those together into multi-scale systems that apply both to longer-term systems of the sort I've outlined, and also to the kinds of structures that can be made in laboratories today. And that means also bringing in the protein engineering software, like the Rosetta design software suite, interfacing all of those. So putting those together would greatly accelerate the ability to accomplish systems engineering development in this domain. The other directions, that's the computational side. The other direction is to focus research efforts in particular areas of peptide self-assembly, of beta sheet stack structures, bring in the more conventional protein engineering for interfacing those structural elements to provide joints between those so you can make frameworks, binding sites for a particular class of photochemically active molecules, people looking at alternatives to this scheme also, but a scheme that would lead very directly to the ability to do nanometer precision control sort of thing that would lead to sort of you could describe it as something like a 3D printer, atomically precise with moderately large molecular building blocks and made batches of 1 trillion at a time. You can see how to do that now. You wouldn't start with $100 billion. Instead, you'd want to rapidly fund some tens of laboratories and then scale up from there as steeply as makes sense. But that's tiny scale. And this particular scheme have not yet looked for funding for that. I think it won't be too hard when we actually get ready to.
You mentioned a lot of low-hanging fruit exists in nanotech. I was wondering which area of nanotechnology you think the fruit will come first.
Okay. The part of the talk where I was using the phrase low-hanging fruit was intellectual low-hanging fruit. I think there's a lot of knowledge that is valuable to have and turns out to be accessible if you understand what the questions are and how to answer them. And that's the exploratory engineering. So the low-hanging fruit there is being able to figure out that, in fact, this makes sense. In fact, this is consistent with everything we know about chemistry and physics. If it weren't true, that would be scientifically interesting. That this itself is not scientifically interesting because it's based on nothing new by construction. In terms of the low-hanging fruit in the development area, the ability to make mechanical systems that give this kind of positional control to guide the motion of building blocks seems to be accessible. The history of molecular technology says that new control of that sort in this domain turns out to be valuable, and valuable in ways that people haven't imagined. So I think I would point at that. And that's essentially what I was just describing.
Okay, I've got a question here. Do I have any other hands? One hand here, and I see two here. Okay, so we'll go in this order.
Thank you, Dr. Drexler. Very exciting ideas. What comes to mind for me is the bacterial flagellum, the machinery for rotation of a bacterial flagellum. Looks very much like one of your molecular machines. So I think it's a very exciting field.
Yeah, that was one of the examples that was prominent in my mind back in the 70s when I began thinking about this. Molecular biologists had found that there were protein machines that behaved as some people describe it as a proton turbine, flow of protons from outside the cell membrane of a bacterium inside, coupled to rotation and a variable speed reversible rotary motor, which is how bacteria swim. Ones that swim have these helical flagella, and there's a motor that turns them. So it's a nice example.
Dr. Drexler, do you think there is room for building obsolescence in APM?
Building obsolescence, in
You
what
know,
sense?
Okay, in manufacturing today, the companies make product to fall apart so they can make more of it. You know, now you have APM. Do you think there is room for this kind of
I think
concept?
that's
like the cars, they don't drive forever. They will fall apart.
That's a good question. Well, the way to think of these technologies, just a first very general rule is look at what people are doing today and the goals that can be accomplished with present technologies, and assume that that's a subset of what, in many cases, is a much larger range that will become possible. With appropriate design or inappropriate design, you can make things that work just fine, and then they turn gray and begin to crumble at the edges, and next week it doesn't work. It's also possible to make systems that are made of extremely durable materials, have large margins, engineering margins in the design, and would last a very long time. It's also possible to design in a way that sacrifices a little bit of strength and performance in order to make the structure consist of small modules that have interfaces that aren't quite optimized and fused for function, but are nonetheless very strong and very effective, but have one additional ability that you can be taken apart again. So that would consist of products that have sort of micro-scale blocks. You can imagine something a little bit like Legos, where you put the blocks together, you have a system, very sophisticated high-performance system by today's standards, and the components can be taken apart, tested. Some of them will have failed, various damage mechanisms. Recycle those, and have a bunch of blocks which for very low energy cost and very rapidly could be remanufactured. So there are prospects for durability, obsolescence, recycling. Also with some additional sacrifice in performance, but still very high by present standards, one can make wide range of functional systems that have the property that they degrade into material that earthworms would think was just fine.
You seem to have focused on atomically precise manufacturing, but what about the role that molecular self-assembly would kind of play? Because it's, particularly if you're kind of imposing designs on atoms and molecules, what about the research focus, which there are groups doing, in taking inspiration, say, from biological systems and kind of letting thermodynamics play its course and structures coming out of that instead?
Yeah. Thank you. I can see that I omitted from my talk a very important area that is very often in my talk, and you've now said, hey, you forgot that. Yeah. The action today in the areas that I outlined of atomically precise fabrication are based on self-assembly. The area of progress, the areas that I've been thinking about extensively and in depth, are applications of self-assembly. My initial work saying, hey, you should be able to design protein molecules that fold, that's a kind of self-assembly also. So those are very much the center of what I think are the most important atomically precise fabrication technologies today. I think that those technologies can be leveraged to incrementally get more control over assembly, that will be valuable and eventually go much further than self-assembly can. But it's where the action is today. Very lively area, and it's, I think, the road forward. I'd like to say just a couple of words about self-assembly. I just don't like the term. It's sort of mysterious. How can, something doesn't exist until it's assembled, so how can it self-assemble because it has to assemble itself when it doesn't exist, and it sounds sort of mysterious. I think a more clear term is Brownian assembly. Brownian motion is the motion of small particles and molecules under thermal motion in a gas, or in this case, in liquid. You know, molecules in a liquid are moving around very rapidly. Larger particles move around more slowly, but they partake of the same thermal fluctuation and motion. So in manual assembly, I use my hand and I put something someplace. In robotic assembly, you have a robotic mechanism that puts something someplace. In standard high-throughput manufacturing, you have devices that simply, in a relatively smooth way, put things together. Brownian assembly uses Brownian motion to put things together. The motion comes from thermal fluctuations, and the trick is that the surfaces have to match and bind in just one way. Basically, you design your structure out of a set of puzzle pieces, and the puzzle pieces have the property that if you put them in a box and shake them, when two of them come together that fit, they stick. And because things happen very, 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 very rapidly at the molecular scale, and one can design surfaces that stick properly, that process actually works in the molecular world. And it's not mysterious.
Hi, Dr. Drexler. I'm just wondering, economics tells us that if a process becomes more efficient, we tend to do more of it. So I was just wondering how efficiency, or the kind of paradox of efficiency, as some economists have called it, is kind of how you see nano interacting with that.
Well, again, it's a matter of potential. The architecture of the book, I start with questions of knowledge. Then what does physics tell us about small devices? What does engineering tell us about what can be built with those? What kinds of materials can be made? What kinds of systems can be made that people might want to make? And then very cautiously creeps up on asking the question, what are people likely to do given the drives that we see in the world today? What sorts of developments either will happen or won't happen because they're blocked? So that's not a prediction. It's going one step beyond physics and engineering analysis to talk about possible developments, but they're developments that, not saying they will happen, but saying they will either happen or they won't happen for a reason that has to do with human action. For example, there either will be an arms race in this area or something will be done to avoid it. Either people will apply tremendous productive capability to go out and pave the earth with whatever, or there will be regulatory frameworks that prevent it. And if there are regulatory frameworks that prevent it, taking the environmental case, there's a prospect of both expanding production from the point of view of giving people what they want and greatly reducing the scale of the human footprint on the earth. Decreasing resource consumption, decreasing emissions, repairing some of the damage already done, reducing the area that is devoted to agriculture today, which can turn over, human race today uses a very large fraction of the net primary production of terrestrial photosynthesis. The areas that used to be species rich and diverse are areas where you can grow plants very well, and those areas, by and large, have been turned into farmland. So one of the best things that one can do for the biosphere would be to increase agricultural productivity per unit area enormously and back off from a lot of the land that has been paved over with soybeans and the like. So that's sort of talking around the general subject of people expanding what they do using greater productivity. And I think the general answer is that people can get what they want while actually having less impact, but with the capability to have enormously more impact, and the way to prevent that is by means of societal controls.
Just one next question. Can I see a few hands? I've got a question here. Anyone else? Okay, can you go ahead?
Hi, I just wanted to know, like, we were talking about like how policy is affecting the advance of the nanotechnologies, but as a scientist, I'm also interested in, like, do we actually have like a solid scientific framework to actually be ready to start doing all these improvements, or do we have to change things in our mindset to actually get there?
There is a shift in mindset that is necessary, and there's a chapter in the book that discusses it, and background to that is in the chapter that discusses the clashing concerns of science and engineering. You can spend, so some scientists are excellent engineers. We had physicists who design experimental apparatus like the Large Hadron Collider, and the detectors for that are state-of-the-art, excellent systems engineers. Some engineers do some excellent science. They have to understand new physical phenomena in order to accomplish new goals, so they do science. But nonetheless, one can draw a line between science and engineering as activities, where science is studying nature and simple phenomena, engineering is composing things to build functional systems. You can do science forever, science in that sharp sense of studying things, and making small laboratory specimens and things. You can do that forever, and you never end up with a complex engineering system. There's a section in the book. Actually, I was going to read a piece at the end, and I forgot to do that. But I think I'll get back to that perhaps. There's a section where I have twin parables of science and engineering. One is titled The Blind Scientist and the Elephant, and explains how scientists who have very limited ability to sense things in a certain area, as we do, have all scientific specialties, can nonetheless put together a coherent picture of an elephant by understanding pieces and publishing in the Journal of Elephantology and Megabeast and Pachyderm Letters and these famous journals, and put together a coherent picture because there is an elephant. And then the twin parable is the blind scientists in the automobile, where our scientists study pieces of, and actually do some engineering. They study various pieces of some idea of an automobile. And you end up with large wheels and small wheels, and engines that are steam engines, and engines that are animals running on a wheel, because we want a bio approach, and just an endless range of pieces that will never, ever, ever, ever fit together to make a Model T Ford unless the people who are doing the work are organized in engineering teams with a top-down structure saying, here's the concept, here are the parts, let's make them and fit them together. The molecular sciences will never develop, if the way they're currently structured, will never develop complex molecular systems engineering products because that requires molecular systems engineering, which is not science per se, any more than the Large Hadron Collider is physics per se. And so when you ask about the change that's necessary, the necessary change is to bring a systems engineering methodology to a sector of the molecular sciences so as to be able to build on the tremendous capabilities that have emerged at the level of components and processes.
What timescales do you reckon this will all be working on? When do you envisage we'll actually have some molecular manufacturing?
Sooner than I expect, I think. Does that mean something? I think that means something. I can imagine scenarios in which the timelines, many different kinds of work can be done in parallel. So you say, well, it'll take a decade to do A, and a decade to do B, and a decade to do C. But in many cases, those decades can be overlapped with a small stagger. And going down that line of analysis and imagining large-scale resources of the sort that have gone into other technology projects that actually have less payoff, one can make stories that lead to timelines from commitment of major resources to results that are short enough to be scary. On the other hand, we've seen people have capabilities that could have been put together much more effectively for many years, and there's been ongoing delay, a rising tide of technology, but a delay in the systems focus. So that's a way of saying it's very hard to predict, but with the focus, there are two kinds of conservatism. If you're thinking about benefits, the conservative assumption is slow development. If you're thinking about disruptions, the conservative assumption is fast development. And I think that's important to keep in mind. So when I say potentially fast, that's perhaps conservative.
As I remember Engines of Creation, there's a whole section about medicine and how all this technology could completely transform medicine, but I don't think you said a word about it today, so is it still, in your mind, another very important application of these?
Yes.
And just curious why you didn't talk about it and how it fits into the bigger
It gets
picture.
people too excited, you know. There's a problem with too much excitement and people being inflamed, and that tends to make other people look at it and say it's, sniff and say that it smells bad, for good heuristic reasons. But it should be obvious. Our bodies are made out of complex molecular systems, molecular machinery, molecular structures. What medicine is about in pharmaceuticals is making molecules that go in and perturb these systems. What genetic engineering is about is going in and modifying the structure of some of these molecular components. What regenerative medicine and tissue engineering is about is poking cells at the level of their molecular regulatory components and environmental signals to make them do different things. If you have the ability to build complex systems that are a superset of biological capabilities of sensing, a superset of biological capabilities for integrating information, A and B and C and not D and above threshold Z, if those then do such and such, if you have the ability to build systems of that sort, it's clear that you expand the envelope of what can be accomplished in medicine enormously. The theme of the book, however, is very much centered around manufacturing, and I mostly talk about things that are extraordinarily simple and ordinary, except high productivity and better materials and faster deployment. But that's only a fraction of what's possible. Which now provokes me to look for a little piece here. There's a section which at least one reader liked quite a lot. It's titled About Enthusiasm. This isn't something I intended to read. There's something that I feel I must say to some of my readers, and I hope that they will understand a somewhat counterintuitive message and take it to heart. If you find these ideas about perspective technologies compelling, convincing, and exciting, if you imagine vistas far beyond any I've outlined, or see solutions to urgent global problems and feel an urge to share the full measure of your excitement, then please lie down until the urge passes. In the world as it is, this kind of excitement triggers a negative response, and for reasons that usually make sense. Almost all grand ideas proclaimed by excited proponents turn out to be wrong and are generally discounted without consideration. If you want to make a positive difference, please help to keep fundamentals first. The chapter is about here are fundamentals that need to be hammered to keep conversation reality-based. Please help to keep fundamentals first, help to correct mistaken ideas, and join the conversation without shouting. And for other readers, please help to keep enthusiasts grounded and remind everyone else that feverish, misinformed people must not be allowed to set the agenda by provoking a backlash or by fostering a kind of guilt by association. To allow this would amount to granting such people the power to control the agenda, but with a minus sign. This has happened before and must not happen again. So this is another allusion to the intellectual / political disaster that we're living in the aftermath of. And why haven't you heard more about this? Well, a Nobel laureate assured everyone that it's really about little tiny robots that might eat you, but it's impossible. And people hear nanotechnology, Drexler, oh, that's about little tiny robots that might eat you, but it's impossible. Can we please forget about that and talk about something real? That's what I'm trying to do in the book, is to reboot the conversation. And okay, I was threatening to read just a couple paragraphs at the end. Okay, here we have the end. Will the outcome of the APM revolution, in fact, look anything like this? Understanding, confusion, choice, time, and chance will all have their say, and with a measure of wisdom, what follows may, in some measure, reflect our intentions. Outcomes aren't carved in stone, in part because human vision and choices are beyond prediction. As perceptions change, possibilities and politics change with them. While new media are transforming the discourse that shapes those perceptions, unexpected new visions have again and again led societies in unexpected directions toward surprising opportunities, problems, and sometimes solutions. As we sweep forward into the quickening rapids of history, will we find a safe course to a world worthy of the hopes of past generations? Neither success nor failure can be assured, but I am persuaded that our choices will matter. And the first choice that matters is what to say, and to whom, today. What is your plan? I would urge you to help to nudge other people into thinking about this and begin to have conversation about the future. Include little footnotes that say, and then there's a possibility that's been suggested that things might be very different. And then the next year the footnote might be expanded into a little paragraph. And eventually one finds reports, and eventually you find that your national security people have entire scenarios for the future that hopefully are not confused with present scenarios. And eventually the perceptions of the future and what is politically possible change dramatically. And the direction in which it changes will depend a lot on perceptions, and there's some enormous pitfalls that scare the hell out of me. And they have to do with people getting confused and acting against their own interests, which is why I wrote the book.
On that slightly sobering note, I'm afraid that time has run away from us a little bit. I do apologize to those of you who still have further questions to ask. Perhaps you can speak briefly to Eric at the end. I would like to ask you to join me in giving a warm thanks to Eric for an absolutely fantastic talk.
Thank you.
I should mention that the book is available here at the back of the room to buy. That's correct. While you're here, there are a couple of events coming up that I think might be of great interest to quite a few of the audience. Next week, we have Professor David Christian the author of the idea of big history, giving a talk entitled Big History and the Place of Human Beings in the Cosmos. And the following week we have a talk no less significant but on a smaller time scale from Andrew Haldane, who is Executive Director of Financial Stability at the Bank of England. He'll be looking at the global financial system and asking if it's safe. The Oxford Martin's seminar program has also started up on Thursday afternoons, which is called this year Blurred Lines, and it'll be investigating the changing role of humans